Hello, guys and gals. Welcome to video on 5.2c. In this video, we're going to be talking just about what orders of reaction are and what they mean, and then also we're going to see what they would look like in a rate law expression. Now, in the last section, 5.2b, we did talk about rate law, and it's important for us to remember that rate law looks like this. Rate is equal to K times the concentration of A to its order times the concentration of B to its order. Okay, and that's what we're going to be talking about in this section. So, the order of a reactant basically tells us how changing the concentration of this reactant is going to affect our rate. So, this is basically a shorthand way of saying, hey, if you double the concentration of this reactant, here's how your rate is going to change. Okay, so it's giving us that concentration because the fact is, or that relationship, because the fact is that not all reactants contribute to the rate the same way. Some of them contribute more, some of them contribute less. In fact, some of the reactants don't contribute at all to the rate of a reaction. And so that's what the order of a reaction is going to tell us. Now, there are orders for individual reactants. Normally what they're going to say there is the order of the reaction in relation to this reactant. So you have order of the reaction in relation to this reactant. Now that's way too much for me to say every time I want to talk to you about it, so I'm just going to call this the order of the reactant, okay? The order for a specific reactant. You can also have the overall order of a reaction, which is going to talk to you about all of the orders for every reactant and how that contributes to the rate, okay? So again, in this video, all we're going to talk about is what the orders are, what they mean, and what they look like in a rate law expression. So the first type of order that you can have for an individual reactant is zero order. You can also have it for overall, but right now we're just going to talk about individual reactants. What that means is it does not matter how you change the concentration of this reactant, nothing is going to happen to your rate. There is no relationship between the concentration of your reactant and the rate. So in a rate law, what this is going to look like is if here's our reaction, A breaks down to B plus C. We only have one reactant in this reaction. The rate law is going to end up looking like rate is equal to K, and if we stick this in here, it's going to be raised to the 0 power. Now the thing is, anything raised to the 0 power just equals 1. It doesn't matter what the number is, it's equal to 1. So most of the time we're not going to write it this way. Most of the time, if our reactant is 0 order, we're just going to leave it out. Because remember, 1 is a value that we normally make invisible. We assume that everyone knows that it's there. And so here's our rate law if our only reactant is 0 order. Notice that the concentration of that reactant is not involved in our rate law. So it doesn't matter what the concentration of that reactant is. You can double it, you can triple it, you could increase it by a factor of 50, but the rate would stay the same because a 0 order reactant has no relationship with rate. It does not matter how you change it, nothing's going to happen. You can also have a first order reactant. Now, a first order reactant means that rate and concentration are directly proportional. They are directly proportional. So if you double the rate of that reactant, the concentration of that reactant, you will double the rate of the reaction. In a rate law, for a similar reaction, it would look like this. Rate is equal to K times the concentration of A to the first. Or again, because we normally turn that 1 invisible and assume that everyone knows it's there, this is more likely what you're going to see for a first order reactant rate law. So, however you change the concentration of A is how your rate is going to change. If you double the concentration of A, your rate is going to double. If you triple the concentration of A, your rate is going to triple. If you quadruple the concentration of A, your rate is going to quadruple. So a first order reactant means that it is directly, that reactant, the concentration of that reactant is directly proportional to the rate. The last common reactant order can be second order. Now, that's not to say that these are the only three orders that a reactant can have. Third order reactants exist, and even fractional orders exist, but we see them very few and far in between. So, second order is the last common reactant order we're going to see. Now, second order can be kind of difficult to understand. So instead of trying to write out exactly what it means, I'm going to show you via rate law. So if our reaction is A breaks down to B plus C, and we find that A is a second order reactant, here's what it would look like. And here's what would happen if we were to double the concentration of A. We would quadruple the rate. If we were to triple the concentration of A, we would increase the rate by a factor of 9. If we quadrupled the concentration of A, we would increase the rate by a factor of 16. And so, however we change the concentration of A, that value is going to get squared, and that's how our rate will change. That's how I have to say that in order for it to make sense to me. You can come up with however you need to think about it for it to make sense to you. But every time that we changed the concentration of this reaction, that factor was squared, and that's how our rate changed. And that's what second order means. A second order reactant is going to highly affect your rate, because however that reactant's concentration is changed, that value is squared, and that's how your rate changes. So those are individual reactant orders. And you can have, let's say, I think the example that I use in the reading is the reaction nitrogen monoxide reacting with oxygen to produce nitrogen dioxide. So we have two reactants in this case. So they could have the same order. They could have different orders. One of them could be 0 order and the other could be second order. And so if we had some experimental data, what we would find out is that NO is second order and O2 is first order. So if we were to write the rate law for this reaction, we would say rate is equal to K times the concentration of NO squared times the concentration of O2 to the first. Or again, you can leave that 1 out. That's normal. That's what a rate law would look like for a reaction that had multiple reactants. Okay? This is also going to lead us into the last part of 5.2c, which is the overall order of the reaction. The overall order of the reaction doesn't really tell us anything specific. It's more like giving us an idea of how sensitive our rate is in comparison to the concentrations of our reactants. So if we were to change something, how sensitive is our rate to that change? All you do for the overall order of a reaction is you just add your individual ones up. So in this case, 2 plus 1 is equal to 3. This is the overall order of the reaction. What that's going to tell us is that this rate is pretty sensitive to changes in concentration. The lower this number is, the less sensitive the rate is to changes. And that's all the time I have, but we are at the end of 5.2c, so let me know if you have any questions, guys. Maybe.